We're going to learn about Elasticsearch today. It's sort of like what's the latest and greatest in Elasticsearch, especially with emerging use cases like AI, RAG, vector search, all those good things, and how Elasticsearch is evolving to meet those use cases. Two quick bits of commercial business. I have in October, there's going to be my next Cheat at Search with LLMs class. There's a discount code for this that gives you 20% off Elastic Rocks, and you'll get an email with that if you don't remember it. And then Trey Granger and I just announced that we're doing an AI-powered search course in November. And that has a early bird discount code of SearchyBird. So for those who don't know me, I'm Doug Turnbull. I host a lot of these lightning lessons, and one of my favorite things to do is to get people from a lot of the search engine vector database companies on, talk about what they're doing, because a lot of the interesting development in this space is really happening with them right now. And so I encourage everyone to listen to Philip. Philip is from Elastic. He's does DevRel at Elastic. I'll let you introduce yourself a bit more, but yeah, turn things over to Philip and learn more about what Elasticsearch is up to these days.
Cool. Thanks a lot for having me. It's by the way great that you wear the 2016 hoodie. I joined 1 month after that, so I've been with Elastic for since 2016. It feels almost like forever. A lot of things have changed in the search ecosystem. I feel like we've always done search and retrieval in general, and now everybody else tries to do that as well, which is great. So I'll show you a bit of like an overview of what we have and what we can do. I have some of the more established things, and I'll show you some more cool of the upcoming things as well. Let me quickly share my slides. There we go. So I think Doug gave this the title Underrated Elasticsearch for Vector Search and AI. And I hope we're not that underrated, but we'll see. Which prompted me to create this stupid take of why shouldn't I just use Elasticsearch for my retrieval overall? So we'll keep this lighthearted. If you have any questions or any comments, let me actually open up chat on the side. If you have anything, unmute and shout, or I have the chat on the second screen. So if you have anything, just interrupt me. I'd love to keep this engaging anyway. I don't just want to do a monologue for a full hour or however long this takes. So I'll try to show you a couple of things. So where we are with retrieval, this is my way of trying to explain the retrieval space. And you can also let me know if you think this makes sense or this doesn't make sense. There's a lot of different terminology going around, from hybrid search, semantic search, lexical and keyword search. This is how I normally try to describe it and combine all of this. So we've done full text search, we've done for a very long time. The lexical keyword search with match is kind of like the original gangster, the OG of search. Though rank features, how you can influence the ranking of things, have been a factor as well for a long time. This is what I would put into kind of like this classic full text search bucket. And then there is the newer bucket of semantic search with sparse and dense vector embeddings, with, I don't know, generally called vector search or learned sparse retrieval. This is the newer group. The thing that sometimes gets people confused is like, these three here are actually all sparse vector embeddings in the technical sense, and only this one in dense vectors. And most of the time when we talk about vector representation or vector search, people mostly talk about dense vector search. I'll also mostly dive into this part for dense vector search here, but we do cover all of these, and all of these are part of the search or retrieval space. So I would always put all of this into retrieval, and then you can combine all of this in hybrid search, where you either boost individual signals or search queries. You re-rank, you have some way to blend them together, like RRF, the reciprocal rank fusion, or you have a script score to blend them together. But all of this is retrieval. We want to find something. I think we've been past the thing where it's like, oh, it has to be dense vector search for RAG, for example. The R in RAG stands for retrieval for good reasons, I would say, because all of these is like, it doesn't really matter how you get the data, but this is really the retrieval space overall. Or maybe to slightly zoom out one level further, I sometimes expand this even further. It's like there are Boolean filters here as well to kind of like narrow down your search, which could be like geographic filters. It's like only give me things in a certain distance, or it could be how recent something is, or any other metadata filtering that you could do, which is potentially called Boolean search. You could do almost the opposite, where you expand it through joins, and Elasticsearch nowadays has joins as well. So you can add different indices or data from different indices together to make that search more expressive. And then the thing that we often don't talk so much about in search is like, all of this can still be wrapped in aggregations to figure out like what is the overall sum or the abbreviation of what we have here. And for us, this is still a retrieval problem, that maybe the thing that you want to retrieve is an aggregation of some combination of what you have collected here. So all of this I would describe as like the retrieval space and what Elasticsearch is doing nowadays. So with that, let me dive into what we actually want to cover. I've broken this down into approximately 4 different pieces that we can do. This is also a reminder for myself to not forget any of these. So I'll start a bit with like, how do you interact with that, and how do we see what we started with, the classical keyword search and match query, and how we see that with semantic text and nowadays retrievers to search that. I'll dive a bit into the internals, like what does it actually look under the hood, and why there is a lot of interesting development, but we generally try to kind of hide it from you because you shouldn't have to know it. We always try to make it simple first. And then basically, if you want to or have to, you can pull back all of these layers to see what is happening under the hood. And you can tune 1,000 knobs there basically, but you don't have to. So we'll look at that. Then we'll go a little bit to RAG. I assume most of you have seen more RAG demos than you care for at this point. So I won't spend too much time on that. But if you haven't seen it, we have this playground to make RAG interactions a bit simpler. And I can quickly show that. And then probably no talk today would be complete if I wouldn't touch on MCP and agents. And that is a bit forward looking because we have some stuff behind feature flags that you can actually start using today around MCP and agents directly in Elasticsearch, but we'll get to that in a moment. And as you can see, I only have 6 slides in total. Only the internals will use another slide. The rest will just start doing live here in queries. So if you have anything, once again, stop me at any point in time. Actually, let's go to console. Is that large enough, or should I make this a bit larger for you?
Good.
Pretty good. Okay. We can actually, I think I can fold this in for now. Somehow I have broken my command plus, but I hope this is good for everybody. This is running on Elasticsearch serverless. So if you ever run into a version that says 8.11 and serverless, this is actually pretty much the master branch right now. This gets deployed every 2 weeks or so. So this is the very latest. This is ahead of what is in a released stack version at this point. But I'm just lazy and let this run, and it shows us the latest and greatest. If you've worked long enough with Elasticsearch and you know keyword or full text search, I always start with the underscore analyze endpoint. Is like, for a keyword search or lexical search, if I have the classic Star Wars quote, these are not the droids you're looking for, and we analyze them for keyword search, I have, these are emphasis dash, not emphasis dash, the droids you are looking for, which is not great. So we'll customize the mapping, and you see in a moment where this goes when we bring this over to vector search and AUY vector search, but also to kind of like keep the interaction of all of this pretty similar. So I'll create a standard mapping. I throw out the HTML tag, lowercasing, stop word removal, snowball stemming. That's pretty much it. So I'll create my Star Wars index. And now if I run it against that, it gives me droid, you, look. So these are the remaining tokens, stop words removed, stemmed down, classic full text search of what this would be doing. So we can actually store this document and the other example that I have, that no, I am your father. So we actually have two documents in our index. We keep this very simple. This is like the hello world here. And then you can do a search, and I assume all of you know why droid matches. These are not the droids you're looking for, because this also gets analyzed. So this gets lowercased. This will get stemmed. So we have droid in the stored document, in the search document, and we have like this direct match in our inverted index, so we can retrieve that. But the interesting thing here, I think, is more around the ergonomics, that you throw a document here with this text against it, and then you simply write a query match, the field name, and then what we are searching for, a droid. And we'll try to bring that over to our vector search to keep that very similar, so that you barely need to know the difference, or like how the internals work. And the classic example of why this doesn't work, if we have like a mismatch in terminology. So somebody searches for robot, and with our keyword search, it will not find the droid, even though probably the droid is a robot that maybe should be found here. So let's add some semantic search. And to keep this simple, I have already added this, so I don't need to expose my API key. But to bring external inference to Elasticsearch, we have this new inference API where you can basically connect it. So when talking to Elasticsearch, you don't need to do the inference anywhere else, but you can just send the text pretty much like we used to do for the analysis. Pretty much with the analysis here, where we just need to bring our text, and Elasticsearch does the analysis under the hood. We want to be able to do the same thing. So this is where our inference comes into play, and I'm adding an external model just as an example, and I'll show you everything else here. So I've already added this before. Everything else is already built into at least the serverless version, maybe the hosted version. On-prem, you also have this one built in by default if you have the right features enabled. So we have multiple inference types. So this is a sparse embedder. You can see by default, I don't have to specify anything like that. There is a chunking strategy enabled by default. This is one of these things that I meant before, where I said, like, we'll give you good defaults. If you need to kind of like tweak those or bring your own settings, you totally can. So you can change the strategy to Word, for example. You can define the chunk size and the overlap. So you could tune that, but these are the default values that, depending on the model, will come here. So for example, if I scroll down, this is a built-in dense vector model, E5 small right now. Somewhere we'll get back to our chat completion model later. We have a re-ranking model, but this is the one that I've just added here. And you can see I only added these settings, and it had like this chunking strategy by default here. I could have added the chunking strategy if I wanted a different one here, but not necessary out of the box. This is just what we give you by default. Okay, now to put all of this together, we'll take a similar mapping like before. And what I'm adding here is I'm using copy2. So I basically interact with my document just like before. We'll keep the same quote field, but we'll also copy that data to an elsewhere field. Like this is the sparse vector representation, and then we'll have with OpenAI, we'll have a dense vector representation of this same field as well. So let me create my index here, and now fingers crossed that everything works. We'll just reindex my existing index into the new index with my two documents. Hopefully this worked, but that one looks good. This again is a hello world example. Your reality will look a lot more complex, but this is just to get you started here. So if I look at my documents, there's really nothing different than before, even though under the hood, I have these different representations here. As you can see, I have my quote Elsa field with the Elsa representation, and I have the dense vector representation. But if you retrieve a document, you don't even see those. Also, because most of the time, you really don't care about like the dense vector representation or the sparse vector representation. All of this is abstracted away. You can get to them if you want to, but by default, you don't have to care about any of that. And then if we now search for robot on the match field, obviously this is still doing the keyword search and robot is not matching here. But if we either search for the robot, it will use the ELSA representation, so that this sparse representation, where it's basically like a keyword expansion, that it will expand either the search text or the index text to something where the two kind of like match. Or you could do the vector or the dense vector representation, either one of these matches. And the only difference, by the way, here from our classic keyword search query is that we just need to target a different field, but otherwise the query and the match are really the same. You don't need to provide like a dense vector representation to search the dense vectors, but the inference service will do the dense vector representation of robot here, and then we'll look up the dense vector representation stored in Elasticsearch, find the most similar one, and retrieve the document without giving you all the additional fields that are there. So all of this is kind of like hidden under the fields. Yes, the inference service, it's like this underscore inference. Let me pull that up again, where did I put that here? It is pretty much like the analysis pipeline in the keyword search world. With keyword search is all built directly into Elasticsearch with the models. They're not running in the same way there, or it's like a bit of a different approach. But yeah, it's all built into Elasticsearch and kind of like behind an API. But these inference services will then reach out to either like, this is like on-prem, for example, a machine learning node, or also on serverless right now, a machine learning node. We have, this is a service that we provide for chat completion. We'll get to that in a moment. But yeah, there might be different services or even external services like OpenAI, but all of that is kind of like hidden behind this underscore inference API. So you never have to think about that or even worry about that. All of that is then kind of like wired together in the background, and you just interact with your documents the same way as you have before. Like you just know, like this is the right field to do the dense vector search, and then everything happens behind the scenes. So the question, how easy is it to hook custom embedding models into it? So if I start searching in our docs, I'll probably get lost. The inference service here, there are multiple services. I think we have like 5 to 10. It's like Hugging Face is an option. So anything that you have on Hugging Face, you could run there. OpenAI, Claude, Bedrock, and a couple of others. All of those are supported. So any model that you can run on any of these, we would support through connecting it here. And you could, by the way, also if you have Ollama locally, Ollama has an OpenAI compatible API. So you could, I don't provide like the endpoint here because OpenAI just used the default one that is online, but you could provide the endpoint, which could be localhost, whatever port Ollama runs on by default, and it would then resolve that locally. So anything you can load into any of these ways to run a model, you could connect through that inference API. I hope that answers the question. So yeah, for this next question from RK, when we use this inference search, if you do a search, this one goes against the keyword field, so no inference endpoint is here in play. But here, quote ELSER, it knows that this field is connected here to an inference ID. And so when you target a field like that, it will automatically use the configured underscore inference endpoint to resolve that at query time for you. Then I have the question, is sparse vector dense vector representation feature for semantic search intrinsic to the language model used here? Yeah, so the model is specifically or specific to either a sparse or a dense representations. So if I go here, depending on the model, it will either be a sparse one or a dense one. And for example, for the dense one, depending on the specific model, it will also give you a specific number of dimensions. So that is intrinsic to the model, if I understand the question correctly. So based on the model you want to use, you need to pick the right representation here that you will store at the end of the day. Then I have the question for ELSA match, since the model produces vectors of terms, is it still a quasi-inverted index type of match? It kind of is. This is maybe a bit of a crude way of explaining it, but think of it as a huge OR query. It's basically we expand one term to 50 to 70, or like if you have one chunk, we expand that to 50 to 70 related terms that is learned from a model, but we'll expand that for the stored part to 50 to 70 models, and your query will also be expanded to 50 to 70 terms. And then we basically do an OR query for these in the query, the 50 to 70 expanded terms, and we'll run that against all the stored sparse vector representations. So it's kind of a huge query that is the kind of like the cost or the downside of sparse vector embedding is that it's potentially targeting a very large subset of your data, just because this expansion of 50 to 70 OR terms can hit a very large point of your or part of your data set. In newer Elasticsearch versions, we have something called pruning, where we basically figure out like what is potentially relevant or what is kind of like the point where it's not relevant anymore. And we'll prune or throw away a lot of that or connected clauses if we know that they will not be more relevant than the other ones that we have. So there is some optimization in there, but you can hit a relatively large subset of your data. Like if you have a lot of data and then you have a query that expands to some common terms, you might hit a large subset of your overall data. That is kind of like the expensive part of sparse vector representation. For dense vector representation, the cost is more in memory when you need to keep the HNSW graph in memory, but we'll get to that a bit later. Uh, Thanks, Ida, for the list of these. Yeah, those are the supported inference services. There is somewhere the documentation. If you search for Elasticsearch inference endpoint in the docs, it will list all of the options and how to configure them. Sparse vector representation right now is not available. I haven't tried this, but if you use Splade, so ELSER is kind of like a tuned and optimized version of Splade++. You might be able to use Splade in the model and put that into Elasticsearch, but I'm thinking if this works or not. I'm not sure. I don't think I've ever anybody seen that. In our tests, ELSER is generally doing better than Splade. That's why I'm not sure why you would need that. But yeah, there are other sparse vector representations, but Elasticsearch is generally mostly working with the built-in ELSER one. The other place where Splade is, or where ELSER is really popular is oftentimes we have people coming to us and say like, what is the best vector representation here? And they don't have a model or they don't know which model to choose. And ELSA is kind of similar to BM25, that it works for many use cases pretty well, even if the model is not specifically trained for that use case. So it's oftentimes a very good starting point, and it has like the vocabulary mismatch is not the same problem as in BM25. So you can get more power through this semantic search with it without having to pick the right model that fits, because finding a model that is actually good for your data set and has the right performance characteristics is its own complication. So if you don't want to do that, that is where we have been pretty successful with ELSER, because it's just there and works pretty well out of the box. Though, yes, ELSER is as it is today. I hope we can change that, English only. That is one of the downsides of all the machine learning models. They need to be trained for the specific languages to work. Okay, I hope I have answered everything in chat. If not, let me know and I'll come back to any questions. let me finish my part of the vector representation here. I think this part was clear that automatically we'll use the inference endpoint or we use semantic search where appropriate. But because of this semantic text configuration, you don't need to worry about it. You don't need to say like, this is a KNN query and this is the dense vector representation. This all happens behind the scenes for you. So this is the appeal of like, why we hope that this makes working with semantic search actually a lot easier than in many other systems is because we have that behind the scenes. If you want to work with dense vector representation directly, we still have a field type. So you could use instead of semantic text, you could use dense underscore vector and sparse underscore vector. So we have those fields if you want to work with them explicitly. But with this semantic text, this is kind of similar to the classic text that abstracts this away. Yeah, here I have an example where we do chunking. So if I index this document and this one has a much larger body, this will, I think, be broken up into 3 chunks or so. And if I retrieve the top 1 fragment of this document, and it's maybe not the nicest search term here, but somewhere in here, I think there is what it expands to, I think there is the term kill in here. This is the one that is the highest match here. And this is why this fragment here is returned. And this is just this one fragment, but not the entire block that we've had before. So this is finding the relevant chunk in our data set. And all of this, again, happening behind the scenes, highlighting, it's not really highlighting the specific term because a dense vector representation or in this case, even a sparse vector representation doesn't, or we could potentially highlight the kill, but we don't here. But down here, you see this was the entire source, and this is the highlighted chunk here that we're getting. Okay, and then final piece of this segment, I hope this was not too much. The way how you can interact with this and that what gives you a bit more power for queries is we have this new concept called retrievers, where you can combine multiple subqueries in a more powerful way than you did before. So for example, here, I normalize this subquery with a min-max query and search for droid and give it the weight 2, and then combine this with the OpenAI query on robot with a weight of 1.5, and this one is also normalized, and then we combine those two, and well, it finds my huge document now with all the occurrences of the terms, which I guess makes sense. And you can do other examples. For example, you can do RRF, so you have multiple ways to combine those subqueries to give your queries more power. But the underlying query, again, is just as simple as before. And we can use other Elasticsearch features like explain true. All of those are still available, and then it will explain to you. If I search through the details here, it will give you an exact representation of like how the RRF score of how to blend those 2 subqueries together works, and then why or what match down here. So if you scroll through all of this, it will give you all the details of what matched and how that got blended together. Okay, thanks Woody for answering questions as well. I hope I covered all the relevant ground here. If everybody is good with that, I'll take a step back and go to the second part now. Let's look at how this actually works or is stored under the hood. And here, let me make this a bit larger. Hope this is readable for everybody. Here I'm focusing on dense vector representation because that is one of the more hotly debated topics. And also because this one has so many options. And as a more experienced audience, I hope that you appreciate that it is very simple to get started. And you saw with semantic underscore text, all of this was hidden behind the scenes. But this is what is actually happening under the hood. So if you have a dense vector representation, there are actually three different granularities per dimension that we can take in or store. The default one, or the most common one, is float 32, or the one that has a precision of 4 bytes. But if your model outputs, so this is defined by the model. If your model gives you byte or bit representation, you could store that in a dense vector in Elasticsearch as well. And semantic text under the hood uses this dense vector representation. It's just all wrapped away and kind of like more slightly nicely packaged. So this is what you give Elasticsearch to store. This is basically what the inference endpoint, when we store the document, returned to us. And now this part down here is what we're actually storing, or what is happening in Elasticsearch under the hood. So there are three different data structures at play in parallel. So we have underscore source. This was the representation that comes in, that was given from the model to us. So this is for a dense vector representation, this array of, I think the OpenAI model that I used was very small. It only had 128 dimensions or something like that. So it would be this array of 128 floating values. And to store this, there are three different options how to store this. And we are just changing the default here. So in 9.2, which is the next minor version that will come out relatively soon, this is, by the way, rolled out on serverless already. So what I'm doing here, we'll do this by default for new indices already, is exclude that in the underscore source, we don't store the dense vector representation there anymore, because we actually use it in an index data structure, and I'll get to that one as well. So if we can, by default, we will not store this dense vector representation twice anymore, but only once. And in our recent benchmarks, this more than halved the required disk space for dense vector representation. The alternatives, the previous default or the previous default was enabled, that we did store the dense vector representation explicitly in underscore source, or you could also disable it, but that had the downside. You couldn't then easily re-index the document because you would have to do the inference again, or you couldn't do a partial update anymore because yes, you can update that field, but you need to rewrite the entire document, and without the dense vector representation, you would lose that information. What exclude does is it, at query time, when you ask for it, it will retrieve from this doc value data structure the dense vector representation. But most of the times, you don't need to retrieve that. It's just very bulky and makes your responses much larger for no apparent reason. So by default, this is excluded, but you can change that. We just had a recent blog post on Elasticsearch Labs. If you've never seen Elasticsearch Labs, maybe that's actually something that I should show. So on Elasticsearch Labs, we blog about all of these interesting things that we're doing. And Jim from our team, he wrote the blog post about how we are excluding these dense vector representations now by default. Almost everything that I'm talking about here has some blog post on Search Labs. So if you're really interested in the details, this will show you even more than what I can do here today. But this is just a pointer over there. Okay, so this is the source. Then we have doc values. This is kind of like the index data structure, how we actually can score, for example. You need these doc values. So if you have index true, which is again the default, so the underscored value is always the default. This stores in Lucene the index dense vector representation by default in the format that you add. So whatever representation you store in Elasticsearch here, that is what will be stored in this index data structure. And this index data structure will also be used for exact KNN search. HNSW or IVF, that we'll get to in a moment, also use this. And if you want to rebuild this here, this is the data structure that is being used. And for scoring in general, we'll always use these doc values. Alternatively, you could quantize these, so you basically compress each single dimension into either int8, 4, or binary, saving you substantial space here. But by default, we'll keep the original representation that you give Elasticsearch into the index data structure. Then to actually search all of this, what you're using today is HNSW. This is required for approximate KNN search. So you will retrieve the top values with this. To calculate the final score though, it's actually using these doc values. So when I say this is the scoring part, this is how you retrieve the candidates from your dense vector representation. And this is what will make, if you have more than 10,000 documents, your search fast. You can do brute force with less than 10,000 documents and it will work reasonably well. But if you have millions of documents, you need a smarter data structure to do that, which is to date HNSW. By default nowadays, since 9.1, we use the binary representation and then we do some overfetching of documents. So the binary representation loses some precision, but we basically fetch 50% by default more documents, re-rank them with the original values, and then get very close to the original results. Alternatively, you can use other quantizations, so either int4, int8, and this one should be down here. This was the int8 was the default from 814 plus until 90. And then in the very early versions of Elasticsearch, the full representation was the default, which is just HNSW. So that, depending on whatever your input was, would store this here, but this is very expensive in terms of memory because HNSW, to work efficiently, you need to have completely in memory. And if you have 4 bytes per vector dimensions, and then let's say you have 1024 vector dimensions, to keep this simple, you'll need 4 kilobytes of memory for each single document. So if you have a million documents, you can do the calculation how expensive this is. So that's why by default we quantize, but especially with the overfetching, the result is pretty much the same, sometimes even slightly better, because HNSW is only an approximation anyway. And very soon, we'll have IVF, the more disk-friendly data structure for approximate KNN search. I think it will be called BBQ disk, and then we'll have other quantization granularities for that sooner, but we'll start with the binary one because we've seen such good results here. I'll share the slides afterwards. I mean, I can tweet out the graphics and everything. I'll share that. The last question, is there an HNSW graph per Lucene segment? The answer is yes. The nice thing about like the immutable data structure of Lucene in the segment way is that this quantization stuff works pretty well because we can quantize per segment. The downside of that is that merging HNSW graphs is pretty expensive. So the hack that we're using is that we're basically taking if we merge multiple segments, we'll take the largest segment without any deleted documents and kind of like add all the other ones. So we're not starting from scratch anymore. That was the initial one, but that was even more wasteful than it would need to be. But we're basically taking the largest one and adding the other documents to that because of the immutable nature of Lucene, merging HNSW graphs is expensive. But yeah, there is one index structure for doc values for HNSW per Lucene segment. Those are always per segment. I hope that answers the question.
Yes, you did. Thank you.
Perfect. Yes, I will also share the API calls that I used. I'll just share a gist afterwards. It will be easy. You can just try all of that out. Any questions to the dense vector representation here? If not, I'll keep moving on. So we are going from more theoretical to slightly more hands-on again. Okay, so let me open this one here. So we have this RAG playground, and Is RAG dead? Is RAG not dead? Obviously, RAG is not dead because retrieving private data or more up-to-date data and giving the right context to LLMs is not a problem that is going away. Also, if you provide too much context to an LLM, they often get confused. I'll get back to the BM25 question in a moment. And we have a playground to actually make this interaction here quite nice. So I have loaded some data, or actually, let me show you the data. This is for the next demo. Afterwards, I have collected a couple of hundred MCP servers. Since no talk today would be complete without MCP, I have collected a list of MCP servers. I used this we used this in a hackathon recently, where we basically gave attendees the data set and say, like, figure out with Elasticsearch which is the right MCP server to use for your problem. And then use that MCP server to build whatever application you wanted. So we have like a large collection of potential MCP servers, and they use the MCP servers to do whatever task they had, which was a fun experiment. Like somebody built like, what do I need? Which MCP servers do I need for a bank case? It's like, I look up the location and I look up the weather and I look up how busy the bank is. And there were MCP servers for all kinds of things that they could use. So this is the data set that we have. And to keep this simple here, I have already connected, this is my MCP servers data set. And you can see here, these are all the fields that are in that data set. I want to retrieve the top 3 documents that I have here. I want to include citations. You could customize the prompt here, how you interact with that. And now I can just start chatting with my data just like with any other RAG application. One other nice thing here is in Elastic Cloud nowadays, we have an Elastic managed LLM built in. So I didn't have to add an LLM here to chat with this. This was just pre-configured and is set here. So I could, for example, say, are there any MCP servers for Elasticsearch? And hopefully this works out. So what happened behind the scenes, these were the 3 documents that were retrieved. Actually, let me show you the query. The query template that we're using here is like, we're using the retrievers that I've shown you before. We're using a very simple one. We are using a multi-match query for whatever I'm asking, and then we are just using this config field. But we could say we want to add the description field for this one as well, for example. So this way I can tune the query, or you could rewrite the entire query. Let me regenerate my question now with the tuned query. So it's still retrieving these 3 documents. And I hope there is somewhere Elasticsearch in here somewhere. I don't see it right now, but there should be Elasticsearch in there. And then it tells me these are the 3 MCP related tools that it found. But none of these mention Elasticsearch functionality. That is not the answer that I was hoping for, but at least it's not lying to me. So here in my data set, it didn't have one for Elasticsearch. So you can play around with this. You could change the LLM. You can change the prompt. You can say with or without context. Which fields do you actually want to search? I probably didn't search the right field here to not find Elasticsearch because it's in there. And then at the end, you can actually export all of this, and you can say like, I want to have this in Python, in LangChain or plain Python with OpenAI, for example. And this is the code, including the query that I have here with config and description, with these are the fields that we have, and giving you all of this boilerplate. It even has the LLM model built in. So this makes working with RAG easier because you can experiment with your queries easily, with your prompt, retrieving how many documents, including the context, etc. So this is how to work with RAG easily. I hope that made sense for that use case. Any questions for RAG? And thanks, Doug, for answering the ELSER versus BM25 question in the meantime. Does the retrieval dynamically prune the corpus at query execution times? I'm not sure I follow the question. So I say like, how many documents do I retrieve for the context here in my RAG application? So it does limit the number of documents. If that answers the question. So we do kind of like limit it. I'm not sure if that's what you mean with pruning, but so we do limit the context here. I could also say I want to have like the top 10 documents that I want, and then you could also say like these are the fields that I want to expose. So all of this is configurable. So again, this is more like a getting started guide. You would then probably switch over to a coding tool to fine tune your RAG application, but it will get you started pretty quickly. Yeah, there is a limit on the documents, how many documents you want to retrieve for that. The last question is about the additional instructions to the LLM, few shots or something else. So in this example, I think it's only a one-shot approach. There is a system prompt that is not shown here. We would need to dig that out of Kibana actually, but there is a system prompt that says like, I don't know, you're an expert user and you're trying to find related documents. So there is another system prompt. This is the user provided prompt here that you could tune, but there is a system prompt built into Elasticsearch behind the scenes. But it does not out of the box here it doesn't do few shot. We'll get to few shot when we switch over to the MCP thing, by the way. For Andrew's first question, how to compare experiments? Any plans to add some RAG evaluation metrics? So we don't really have that today. I hope we will. I hope my PM colleagues will not kill me for saying that. We are, I think, generally not in a bad place to do that since we have like all of the observability stack in Elastic with logging and metrics and everything as well. So we should build that. We're definitely looking at experiments, but there's nothing that I can, or there's nothing ready yet for you to use. But evaluations are definitely one of the hottest topics right now, and I hope we can get that out. Our first focus is on agent and MCP. We'll get to that in a moment. But evaluations are definitely on our radar, and I hope we get there, but no promises right now. The last question that I see, tensor sparse which method is being used. Can we do a combination on the use case? Yes. So by default, this one here actually is a different data set. This one didn't have a tensor sparse representation, but you could just add that, or depending on the data that you have, you can do that. And then you can customize your query. So if you have in the stored data, you have a sparse or a dense vector representation, you can customize the query, and then you can do keyword search, hybrid search.
Large language models, they are everywhere.
Or anything that you want. So you can turn this simple multi-match query into an RRF query. Since this is already based on retrievers, you can really write any complexity in terms of queries that you want. I hope that answered that question. Okay, final point. This is agents and MCP. This is right now behind the feature flag. It will be, I think, in 9.2, which is not out yet. So on serverless, you can already get it, or if you build Elasticsearch from source, you would also have it. It's behind the feature flag. These are the commands. I can share the documentation for that. It's in the Kibana repository. So you need to enable, it had the initial internal project name. I think we'll change one chat. But you can enable MCP, agent to agent, API access, UI, and tools. You need to enable all of these in Kibana, but then we ship all of these features directly in Kibana. We also had an MCP server, a standalone one. This one is what you have been able to use for a couple of months already. So this is a standalone binary that runs basically in front of Elasticsearch. So you can run and deploy this, and it has a couple of things built in. But this is not going to be the way forward. So this was just getting us started with MCP. So you have a couple of tools available to interact with Elasticsearch. But going forward, the new way of doing this is these will become stable and publicly available soon enough. But once you have enabled this, you will actually have this new UI point here, which is called chat. And I can show you here, these are the built-in tools of our MCP server. So these are the tools for our MCP server, which can run ESQL queries. It can get documents by IDs. It can get index mappings, list indices. It can use the search endpoint. But the nice thing is we have often relied very much on turning natural language into queries. You can also help the LLMs by providing additional queries here. So for example, we could add something, and this is based on ESQL queries. Let me maybe show you how this works. This will be easier to show here. So here, we have this data set from public service limit 10. This is our pipe query language. This is how you can right now interact with this data set. And we can rewrite this query to do whatever we want. And you can make joins and complicated keyword queries or semantic search queries. I'll keep it simple and I'll do an aggregation because we've been talking about aggregations before. And so you don't have to watch me type this here. Let me remove this. So we'll take from this data set, I want the sum of all GitHub stars in here. And then it will tell me there are 241,000 GitHub stars across all the documents in my data set. And then I can turn this into a tool here. So I can create my custom tool here, some GitHub stars. I think this is, I hope this is a valid name. Count the sum of GitHub stars in the data set. And then we can use this query here and save this. You can also add, for example, parameters where you could say here in the query, there should be a parameter, and you can describe it, and then the LLM can figure out these are the potential parameters in a query, and this is what I should fill out. So I'll keep it very simple and just provide a static query. But this way you can provide any type or complexity of queries as additional MCP tools. And by the way, I have assumed that everybody knows what MCP is. I don't think we'll have time or energy to go over MCP details. I'll point to other courses on MCP, but this is our way of how we think about integrating MCP. So rather than writing a lot of custom code, you can just bring any query here to our tools. So now we have our new some GitHub stars custom query. You could package any feature set into a custom agent. So for example, here I can describe the agent and give it custom instructions and give it some labels and how to display it. A lot of this is in flow and will change. So don't take screenshots and expect this to look exactly the same in a month or so. But this is the general idea that you can provide tools. Then in an agent, you can combine different tools together and say like, these are the tools that we want to expose in here. And then you can start interacting with that. So here, again, we're using this default agent where our custom tool is involved. I can just start chatting with my data. So I could say, what indices do I have in my data set? And so this is thinking for a bit, and then it tells me here it actually, this is, it was thinking about it, and then it figured out it had a tool to retrieve the indices, and then it was retrieving these indices, and then it's giving me this result. And then I could say, do the MCP servers have? I hope this will work out with the LLM. Sometimes it's slightly unpredictable, but ideally it manages to find the right tool, so that aggregation that I've just written, and it will use that to retrieve the number of GitHub stars. Okay, you can see this was the query that I've written and provided. No, it got raw. It started writing its own query. It didn't use my tool. Maybe let me double check. Did I not give this a good description? Because so the LLM uses this description here to figure out which tool to use. But maybe Claude is slightly smarter. Let me restart Claude, because I just added a new tool, so we'll need to restart Claude that it will find that new tool. So we have Claude here, and I have connected Elastic, and some GitHub stars seems to be connected here. How many GitHub stars do the MCP servers have in total? And I hope this calls the right tool now and will give us our result. We'll allow access to this one. And you can see some GitHub stars. That is the function that I wanted to use. And yeah, this one, it used the right function and it retrieved those 241,000 GitHub stars that we have behind the scenes. This is a very simple example of how you can use MCP. But this is how we see of, again, like I've shown with semantic text, that we provide a very simple abstraction on top, and then there are more complicated layers under the hood. It's the same thing here, where we don't want you to write like a lot of code all the time, but we will provide queries and then give better options to an LLM to figure out what you can do with your data. So this is how we see the agent and MCP world working for Elasticsearch. I hope this was useful. I think we're almost out of time. Any final questions?
Going once. I know there's been a lot of ongoing questions. Oh, someone has a question. Oh, Bertrand. Thank you.
Yeah, we did answer a lot of questions. I hope we got through everything. Doug, do I just give you the materials and you share them afterwards, or how do we do that?
Definitely, yeah. And this video will be available, so that we can do both.
Perfect.
So everyone will get a message for this video. So thank you, everyone. Yeah, so I hope everyone has a good rest of your week. And thanks, Philip, for giving us such a great tour. I've got a lot of things to go Google and learn more about now.
Thanks for having me.
Thank you so much. Take care.
Bye, everyone.